Welcome. This is a guide to one of the most powerful ideas in data science, dimensionality reduction. We're going to make a complex topic feel simple and intuitive. First, we need to understand the problem we're trying to solve. It's a strange, counterintuitive world known as the curse of high dimensions. So what do we even mean by a dimension in data? It's simpler than it sounds. A dimension is just a feature, an attribute, a single column of data you've collected for each observation. For example, if you're analyzing houses and you track square footage, number of bedrooms, and age, you have a three-dimensional dataset. Each house is a single point in a 3D space. Why does this matter? Because our brains are wired for a low-dimensional world. 1, 2, or 3 dimensions are things we can see and reason about intuitively. Here's the catch. What happens when you have 4 features? Or 100? Or 10,000? How do you possibly visualize that? So, why do we even bother with dimensionality reduction? It's not just about tidying up. It boils down to 2 huge practical benefits that change how we work with data. First, it lets us visualize the impossible. By squashing high-dimensional data down to 2 or 3 dimensions, we can literally see the hidden structure. Are there groups? Is there a shape? Who are the outliers? This is your first, best tool for understanding a complex dataset. The second benefit is pure performance. Fewer features mean your models train faster. It also helps prevent overfitting by removing noise, so your model generalizes better. And for certain algorithms, it makes the data less sparse and easier to work with. It's a win-win-win. Okay, so how do we actually reduce dimensions? There are 2 fundamentally different approaches. You can either select the best original features, or you can extract brand new ones. Let's break that down. First up is feature selection. The philosophy here is simple and direct. Find the most important features in your original dataset and just throw the rest away. Imagine you start with a set of original features. Let's say there are 6 of them, from F1 to F6. You then use some method to score their importance. Based on those scores, you select a subset. In this case, F1, F4, and F6 were the most predictive, so we keep them and discard the others. The biggest advantage of this approach is interpretability. Because you're still using square footage or crime rate, you can explain exactly what your model is doing. The logic remains transparent. Now for the other path, feature extraction. This is completely different. Instead of picking from the originals, we're going to create entirely new features by combining the old ones. Again, we start with our 6 original features. So, how does this actually work? Imagine we have a bunch of housing features. Instead of using them directly, an algorithm can combine them. Here, it's creating a new, more powerful feature called Component 1, which represents the overall property size by mixing square footage, bedrooms, and lot size. The core idea is simple. We start with a set of original features, maybe 6 of them in this case. Think of these as the raw ingredients. Then, the magic happens. The algorithm learns to combine those raw ingredients into a smaller, more meaningful set of extracted features, like C1 and C2. This is a form of intelligent compression. Here's the math behind that transformation. It's surprisingly straightforward. Each new component, like C1, is just a weighted sum of all the original features. The algorithm's job is to find the perfect weights, the A, B, and C values, that capture the most important patterns in the data. Here's a powerful idea. What if we could create entirely new features that are better than the originals? This is the core of feature extraction. Let's make this concrete. Imagine combining square footage, number of bedrooms, and lot size into one single feature. This new property size component can be a much stronger signal for a model than any of the individual parts. So, let's visualize the process. We begin with a set of raw, original features. In this case, we have 6 of them. The goal is to transform this larger set into a smaller, more potent set of extracted features. We're distilling the information down to its essence. So what's the math? It's surprisingly simple. Each new component, like C1, is just a weighted sum of all the original features. The algorithm's job is to find the perfect weights to maximize the information captured. So what's the big deal with feature extraction? The real magic is its ability to find the hidden story in your data. It does this by capturing the complex, subtle relationships that exist across all of your original features at once. In this tutorial, we'll focus on two key tools for the job. First, the classic and foundational method, PCA, or Principal Component Analysis. Then, we'll explore a more modern and powerful technique for visualization, t-SNE. Welcome to Chapter 2. We're diving into one of the most fundamental techniques in dimensionality reduction, Principal Component Analysis, or PCA. Think of it as the reliable workhorse of data science. So, what's the big idea here? It's simple. We want to reduce the number of features in our dataset, but without throwing away the valuable information. PCA achieves this by creating brand new, more efficient features. The core idea behind PCA is actually very intuitive. It's all about finding the directions or axes within your data that show the most activity, the most spread. But what does spread even mean? In the world of PCA, there's a simple equation to remember. Information equals variance. The more spread out your data is along a certain direction, the more information that direction contains. Here's a great way to visualize this. The shadow analogy. Imagine trying to capture the essence of a complex 3D sculpture with a 2D photo. A bad angle gives you a meaningless blob, losing all the detail. But a good angle reveals its intricate structure. This is exactly what PCA does. It methodically finds the perfect angle to project your high-dimensional data, ensuring the resulting lower-dimensional shadow captures the maximum possible spread or variance. Okay, let's move from analogy to a concrete example. Picture a simple 2D dataset that looks like an elongated oval or cloud of points. The most obvious direction of interest is the one that runs along the longest axis of this cloud. This is the direction of maximum variance, and we call it the first principal component, or PC1. What about the next most important direction? That's PC2. It captures the next highest amount of variance, but with a critical constraint. It must be perfectly perpendicular, or orthogonal, to PC1. Okay, let's get hands-on. The first step is always to load and understand our data. We're using the famous iris dataset, which has 4 numerical features describing different flower species. Here's what the raw data looks like. Notice the 4 columns of measurements. Our goal is to squish these 4 dimensions down to 2, without losing the core information that separates the species. This is a critical pre-processing step that many people forget. PCA works by finding directions of maximum variance. If one feature has a much larger scale than others, it will dominate the analysis, leading to misleading results. The code is simple, just one line using scikit-learn's standard scaler. The result is that every feature is now on the same scale, centered around 0. This ensures our PCA algorithm treats them all fairly. Now for the main event. We're ready to apply PCA. Our goal is to reduce the 4 features down to just 2 principal components for easy visualization. Here's the core of the algorithm. We create a PCA object and tell it we want 2 components. Then, we call fit_transform on our standardized data. This single command does all the complex linear algebra for us. And here's the output. The original 4 columns are gone. In their place, we have 2 new abstract columns, Principal Component 1 and Principal Component 2. These are the new axes of our simplified data. The real payoff comes when we visualize this new 2D representation. We'll create a scatter plot where the axes are our 2 new principal components. This is standard plotting code using Seaborn. We're plotting PC1 on the x-axis, PC2 on the y-axis, and coloring each point by its original flower species. And this is what we get. The plot reveals the hidden structure in the data. Even though we compressed 4 dimensions into 2, the different species form clear, distinct clusters. This is the power of PCA for visualization. Let's recap our first finding. We've established that the first principal component, PC1, essentially acts as a single number that measures the overall size of the flower. So what's the story with the second component? What new information is it capturing that size didn't already cover? The secret is always in the loadings. Notice the huge negative value for sepal width. Negative 0.923. This feature completely dominates the component. Here's the critical insight. Because one loading is so strongly negative, PC2 isn't about size anymore. It's about the relationship between features. It's a component of contrast. So what does that contrast mean in the real world? A high score on this component directly corresponds to a low value for sepal width. In simple terms, it identifies flowers with narrow sepals, and that gives us its name. While PC1 measured size, PC2 measures shape. It separates flowers based on how wide or narrow their sepals are. Okay, we've handled PC1. Now, what's the story with the second principal component, PC2? When we look at the loadings for PC2, one number immediately stands out. Sepal width has a very strong negative loading dominating this component. Here's the key insight. Unlike PC1, which measured overall size, PC2 is all about a trade-off or a contrast between features. The relationship is inverse. A high score on this component corresponds to a flower with a low value for sepal width. In other words, a narrow sepal. Because it's measuring this specific trade-off, we can give it a much more intuitive name. It's the sepal shape component. Ultimately, PC2 acts as a separator, distinguishing flowers based purely on the shape of their sepals, pitting the wide ones against the narrow ones. The biggest mistake people make with PCA is treating it like a magic black box. You put data in, you get components out, but you don't truly understand why. But now you have the essential diagnostic tools. By analyzing explained variance, scree plots, and component loadings, you can finally open that box and see what's inside. This is the critical shift in thinking. You're no longer just blindly reducing dimensions. You're moving from a mechanical process to one of deep, meaningful interpretation. And that's the ultimate goal, to go beyond the algorithm and truly understand the fundamental story your data is trying to tell. That's the real power of PCA. Welcome to Chapter 3. We're about to dive into t-SNE, a powerful technique for visualizing data that lives in complex curved structures. So, why do we even need something beyond PCA? The short answer is that PCA's greatest strength, its reliance on linear relationships, is also its biggest blind spot. PCA is fantastic when your data's structure can be captured by straight lines and flat planes. But what happens when the real structure is curved or tangled? PCA will fail. Let's use a classic thought experiment called the Swiss roll. We take a perfectly flat two-dimensional dataset and simply roll it up in three-dimensional space. Here's the catch. The true relationship between points is the distance along the curved surface. In the 3D view, points A and C look far apart, but if you unroll the sheet, they're actually right next to each other. So what happens if we apply PCA to this 3D roll? It's like crushing it with a steamroller. It finds the best flat plane to project onto, completely ignoring the curved structure. The result is a disaster. PCA flattens the layers on top of each other. Points from opposite ends of the original sheet are now seen as close neighbors. The true local structure is completely destroyed. This is the classic signature of a nonlinear data structure. To solve this, we need a fundamentally different approach, one that can respect the curve of the data. That new approach is called manifold learning. The core idea is to find and gently unroll these curved data structures back into their natural, lower-dimensional form. So what is a manifold? It's just a mathematical term for a shape that looks flat up close, but is curved on a larger scale. The surface of the Earth is the perfect analogy. This leads to a core idea in machine learning called the manifold hypothesis. It suggests that most real-world data sets, even if they have thousands of features, actually lie on a much simpler, lower-dimensional surface embedded within that high-dimensional space. So, what's the big innovation in t-SNE? It's the switch to a different probability distribution, the student's t-distribution. This one change is the secret to creating those clean, well-separated clusters everyone wants. Here's the core difference. A normal distribution has thin tails, meaning it severely penalizes points that are moderately far apart. The t-distribution has heavy tails, which creates more room in the low-dimensional map, allowing these points to be placed further away without a huge cost. The practical effect of heavy tails is profound. It creates breathing room in the 2D map. This allows points that are only moderately similar in high dimensions to be pushed much further apart, preventing the crowding problem we saw with SNE. Let's break down the logic. Imagine two points that are moderately distant in the original high-dimensional space. The t-distribution's heavy tails mean that in the 2D map, their required similarity is extremely low. The result? The optimization pushes them very far apart, creating distinct clusters. Now, what about points that are genuinely close? For these, their high similarity in the original space is preserved. The t-distribution still models them as very similar in 2D. This ensures that the local structure, the tight groups of points, is accurately represented. Here's the core problem we need to solve. In the original high-dimensional space, the similarity distribution is very narrow. This means it's hard to tell if 2 points are truly close or just moderately close. So what's the trick? We intentionally transform this distribution. We take that narrow, pointy curve and flatten it out for the 2D map. This creates more separation. This isn't just a minor adjustment. This single change is the entire secret behind creating those clear, well-separated clusters you see in a t-SNE plot. It's everything. Let's break down the logic. We have two competing forces: the true similarities from the original high-dimensional data, which we'll call P, and the new similarities we must create in our 2D map, which we'll call Q. First, the simple case. If 2 points are very similar in the original data, their similarity score P is high. The algorithm's top priority is to make sure their similarity in the map, Q, is also high. This keeps clusters intact. Now for the magic bullet. What about points that are only moderately similar? Their p-value is medium. The algorithm deliberately forces their q value in the map to be very low. This is the exaggeration we saw earlier. Let's pause here for a moment. The next concept builds directly on what we've just covered. Okay, we've laid out all the individual components and the context. We've seen the problem from a few different angles. This is the turning point. We're about to connect these ideas into a single, powerful mechanism. Pay close attention to how each piece fits into the next. All right, let's get our hands dirty. We've talked about the intuition behind t-SNE. Now let's see it in action with a real-world coding example. The goal is to take on the famous MNIST dataset. Each data point isn't just a few numbers. It's a 784-dimensional vector representing a handwritten digit. Our job is to see if t-SNE can untangle this complexity. First things first, we import our tools: NumPy, Matplotlib, and of course, t-SNE from scikit-learn. Then, we load the MNIST dataset directly. The variable x holds our 784-dimensional image data, and y holds the correct labels. Here's a practical tip. Running t-SNE on all 70,000 images would take a long time. To get a result quickly, we'll work with a random sample of 5,000 images. This is a common and effective strategy. So now our input data, x-sun subset, has 5,000 rows, each with 784 features. The goal remains the same. Turn that 784-dimensional space into something we can actually see. This is where the magic happens. We create a t-SNE object, telling it we want a 2D map. Then we call fit_transform on our data. Scikit-learn handles all the complex optimization steps for us. Let's quickly break down these settings. N-components is our target dimension, 2. Perplexity is the most important knob to tune, and we'll dive into it next. The others, NITER and random state, ensure the algorithm runs long enough and gives us the same result every time. Now let's get practical. Tuning t-SNE is where the magic happens, but it's also where most people get lost. Unlike PCA, it's more of an art than a deterministic science. The single most important parameter you'll ever touch in t-SNE is called perplexity. What is it? At its core, it's your best guess for how many close neighbors each data point should pay attention to. Here's the catch. Perplexity is a trade-off. Set it too low, and you'll see every tiny local detail, but you might miss the big picture. Set it too high, and you'll see the global structure, but you risk washing out important smaller clusters. Welcome to Chapter 4. Here, we're going to settle the debate between two powerhouse techniques, PCA and t-SNE. The goal isn't to pick a winner, but to understand when to use each one. At first glance, both tools reduce dimensions. But here's the catch. They have completely different philosophies about what information is important to preserve. There are 3 core distinctions you absolutely need to know. Getting these right will prevent you from making very common mistakes in your analysis. The first and most important difference is what part of your data's shape each algorithm tries to protect. Does it care about the big picture or the tiny details? PCA's job is to maintain the overall layout of your data. It looks for the biggest sources of variation and uses those to create its map. Think of it as prioritizing the main highways of your data. A great analogy for PCA is a world map. It does an excellent job showing you that North America is far from Australia, but it's the wrong tool if you need to navigate the streets of a single city. Now, t-SNE does the exact opposite. Its one and only goal is to make sure that points that were neighbors in the original data are still neighbors on the final map. It doesn't care about anything else. The perfect analogy for t-SNE is a city's subway map. It's brilliant for seeing which stations are connected, but the distance on the map between the first and last stop tells you nothing about the actual track length. The second key difference is about the complexity of the patterns each tool can understand. Can it only see straight lines, or can it see curves and twists? PCA is strictly linear. It works by rotating and projecting your data. If your data lies on a complex curved surface, PCA will essentially squash it flat, destroying that intricate structure. So what's the standard approach? It's a two-step process. First, you run PCA to clean up the data, and then you feed that result into t-SNE for the final visualization. This is the industry standard playbook. So, which tool should you grab? Use PCA when you're preparing features for a machine learning model. Use t-SNE by itself when you're just exploring the data visually. And for the best of both worlds, a fast, high-quality visualization, use the PCA then t-SNE pipeline. But here's where things get dangerous. These tools are powerful, but they come with traps. Understanding what these visualizations don't tell you is just as important as what they do. Here's the biggest and most common mistake. You absolutely cannot interpret a t-SNE plot globally. The beautiful clusters it creates can be incredibly misleading if you're not careful. First, let's talk about cluster size. You'll see some clusters that look big and spread out, and others that look small and tight. It is a huge mistake to assume this tells you anything about the variance of the original data. It doesn't. The correct way to see it is this. t-SNE is just giving clusters room to breathe to show you the local connections. All you can say is that points within a cluster are similar. You cannot compare the size or density between two different clusters. The second trap is the distance between clusters. It's so tempting to look at two clusters that are close together and think they're more related than a cluster that's far away. This is also completely wrong. The truth is, the algorithm places clusters on the 2D canvas for optimization reasons, not to represent their true separation. All you can conclude is that you have distinct groups. The distances between them are an artifact of the visualization. Here's a great way to remember this. Think of t-SNE as creating a seating chart for a party. It does a great job of putting people from the same town at the same table. That's preserving local structure. But the distance from the New York table to the London table in the room tells you absolutely nothing about the real-world distance between those cities. So, what happens when we apply this logic to our Swiss roll? PCA has one simple goal. Find the direction where the data is most spread out. Here's the catch. For a coiled structure like the Swiss roll, the direction of maximum variance isn't along the curve. It's straight through it. PCA doesn't see the delicate structure. It just sees a blob to be flattened. This is the critical failure. Imagine 2 points on opposite sides of the roll. Along the manifold, they're far apart. But when PCA flattens the roll, those 2 points get projected to nearly the same spot. And just like that, the most important information in our dataset, the continuous, spiraling structure, is completely destroyed. This is why linear methods like PCA can fail spectacularly on nonlinear data. So what happens when we apply PCA to this complex, nonlinear shape? Its only goal is to find the flat plane that captures the most spread. And here's the catastrophic result. Instead of unrolling the data, PCA simply flattens it, like a steamroller crushing a can. The projection is a mess. All the meaningful neighborhood information from the original spiral is gone, leaving just a dense, useless blob. This is the critical takeaway. PCA has no concept of the path along the manifold. It only sees the direct, through-the-air distance, causing points from different parts of the roll to incorrectly appear as neighbors. So, does this mean PCA is flawed because it can't handle curves? Not at all. It's a common misconception. The key is to reframe your thinking. This isn't a flaw. It's simply a core characteristic of how the tool is designed to work. Here's the takeaway. PCA is world-class at one specific job: simplifying data where the most important patterns can be described by straight lines. The real question is, what do you do when your data doesn't follow straight lines? What if the important patterns are curved, or grouped into complex nonlinear clusters? When you see that, it's a clear signal. You've reached the limit of what a linear tool can do, and it's time to switch your approach. And a perfect next step for that is a technique like t-SNE. It's specifically designed for visualization by finding and preserving those complex local structures that PCA would miss. Let's move past the fundamentals. What happens when PCA and t-SNE aren't enough? This chapter explores the powerful alternatives. You've mastered the two main pillars of dimensionality reduction. But the world of options is much bigger, and knowing the alternatives is key. Meet the new champion for visualization. UMAP is often the first tool data scientists reach for today, and for good reason. So why is UMAP so popular? It comes down to three key advantages over t-SNE. It's faster, it better preserves the global data structure, and it's easier to tune. The best part? Using it is incredibly simple. The API feels just like scikit-learn, making it an easy drop-in replacement for t-SNE. Before UMAP and t-SNE, other algorithms paved the way. Let's look at two pioneers that introduced the core ideas of manifold learning. Here's the core idea of isomap. Instead of measuring straight lines through the data, it measures the true distance along the curved surface, effectively unrolling it. LLE, or locally linear embedding, takes a different approach. It assumes that if you zoom in far enough on any part of your data, it looks flat. All right, let's finish this video here. In the upcoming videos, we will discuss other options and how do you choose the right tool for the job. Please make sure to follow the channel and press the like button and give us a comment to let us know what you think.